Hello, this video is for lesson 3.1. For Math 161, we are going to look at inverse function. This is the first lesson of Unit 3. Unit 3 will cover exponential functions, logarithmic functions, but 3.1 is just talking about inverse function, writing how to, finding, what are we doing? Well, determining whether two functions are inverses, and given a function, we're going to try to write an inverse function, okay? But first, let's talk about one-to-one functions. I have a definition of one-to-one function right here, but first, let's click on this link to investigate what one-to-one functions look like by looking at their graphs. Now, this link doesn't work. I converted this document into a PDF, and I can't really click on this. So what I did was I created a link on Canvas. You can find this under your week 11 agenda. I'm opening the one for Monday, Wednesday class, but Tuesday, Thursday, guys, will also have this link. Under 3.1 lesson, inverse functions, you can click on investigating one-to-one functions and their graphs links. Let's take a look at this first, okay? And we'll come back and talk about all these assignments that are due this Sunday. But first of all,
in this animation, please enter 5 ordered pairs that define y as a one-to-one function of x. Use integer coordinates between -6 and 6 in each ordered pair. Then hit submit to see how you did.
And 6 in each ordered pair. Then hit submit to see how you did.
Okay, so let's make a one-to-one function. Well, just say, they said use integer coordinates from -6 and +6. So let me just make the first one to be -6. Next one can be like -5. Let me make it like, I don't know, maybe 0, 2, and 4. So this is what I know already. I know that to be a function, x value should not repeat, right? So look at all the numbers that I plotted. -6, -5, 0, 2, and 4. Now, these x values are all different. So this will satisfy that part about being a function, right? Let me pick some random y values. Anything in between -6 and 6. Let me just do 2, 5. Oh, not t. It should be a number. 5, 1. Maybe like another 2. And then like I'll do -6. So I plotted a couple of these random y values that I just picked. And you notice that the y value is repeated here, right? What's the y value that repeated? 2, right? 2 is right here. Like I used 2 up there. And then I used 2 again down there. Now, this is a function though, right? Because as long as x values are all different, y values can repeat. So this is a function. But the question is this one-to-one? Let me go in and graph this. Now, I graphed this, I plotted this, and then they did this little test for me. The test that they did for me, notice what kind of line they drew for me? They drew a horizontal line. Now, if you want to see if a function is if a relation is a function, you performed a vertical line test. If you want to see if a function is one-to-one, then what you do is this line test called horizontal line test. And it works exactly the same. You draw a horizontal line, and if you have more than one point on that horizontal line, it fails the horizontal line test. Therefore, it is not a one-to-one function. Let's read what they have. The ordered pair does not define a one-to-one function. Please try again. So guess what's causing the trouble here? You see how I repeated the y value 2 and 2? So what if I change that to like, maybe if I change this to 1? Oh, you notice if I just change that to 1, I'm going to fail that horizontal line test again, right? Because I have repeating ones in the output. See, I failed it again. At least 2 ordered pairs have the same y but different x. Try again. So in order for this to pass the horizontal line test, not only my x's have to be different, but my y's all have to be different. So what was the y value that I did not use so far? Let me use 0. So all the x values are different and all the y values are different. If I click,
now click the graph inverse button to see the inverse function.
Now click the graph inverse button to see the inverse function.
Oh, yes. So, when all the x values are different and all the y values are different, none of the x's repeat, none of the y's repeat, then you can say, oh, this is a one-to-one function. Now, let's click on the button, graph inverse, and see what the graph looks like.
The inverse function is found by interchanging the x and y coordinates of each ordered pair in the function.
The inverse function is found by interchanging the x and y coordinates of each ordered pair in the function.
Note that the graph of the function and the inverse function are symmetric with respect to the line y equals x.
And the inverse function are symmetric with respect to the line y equals x.
Cool, right? Now, I think I was zoomed in a little bit when I was watching this. So like when they switch the x and y, they try to put it in the ordered pair, but it's kind of messed up. Like you see how the zero's outside the parenthesis, but you see how they created these ordered pairs, right? They simply switched x and y. But the second part they also mentioned is that the graph, the red dots and the blue dots, they are symmetric with respect to the line y equals x. I want to play this one more time, but then I'm going to try to make it so that the symmetry is a little bit easier for us to see, okay? So give me 1 second. Let me just make it a very basic. I may try to just plot something that only has the graphs on maybe like the second quadrant. Let me try that, okay? I'll do negative 6, negative 5, negative 4, negative 3, and negative 2. I just want to do another set so that I can show you what they mean by the symmetry, because my first order pairs, first one-to-one function, they were kind of everywhere. So I don't think you could really see what they meant by the symmetry. But let me try one more time, okay? With just some different, values. First of all, take a look at what I typed up here, okay? Now, does it look like it's going to pass the horizontal line test? Well, first of all, to be considered one-to-one function, it needs to first pass the vertical line test. And it does, right? Because all the x values are different. Now, not only that, all the y values are also different. So it's going to pass the vertical line test. Let me go ahead and submit this.
Good job.
Now click the graph inverse button to see the inverse function
of x.
So
now click the graph inverse button to see the inverse function.
You ready to see the graph? Now, we're going to ask this lady. She's doing such a great job. We're going to ask this lady to graph or find the order pairs for the inverse function.
The inverse function is found by interchanging the x and y coordinates of each ordered pair in the function.
The inverse function is found by interchanging the x and y coordinates of each ordered pair in the function.
Oh, how lovely.
Note that the graph of the function and the inverse function are symmetric with respect to the line y equals x.
And the inverse function are symmetric with respect to the line y equals x.
Oh, how amazing. Can you guys see if we fold this graph by the green y equals x line, it will be exactly like they will overlap, right? So hopefully this second example kind of shows you what they mean by symmetric with respect to the line y equals x. But using what we just watched together, let's go back and find some, work with some functions who may be one-to-one, who may not be one-to-one. So let me go over here, okay? Let's go back to the notes. Example 1, determine whether a function is one-to-one. But let me go ahead and read this definition of one-to-one function first, because I typed up the definition over here for you. Now let's see. If a function f is one-to-one function, if for a and b in the domain of f, if we have two different input values will give you two different output values. What they are saying is, if you plug in different x's into this function, you are going to have different y values, okay? So a quadratic will not be a good example. Because take a look, if you have a quadratic function, simply y equals x squared, say that you have that. Then, just couple x values, you have -1. Why am I making this so small, right? Say that I have -1, 0, and 1. If you plug in -1 into this function, you will get 1. If you plug in 0 into this function, you will get 0. Plugging in 1 will give you 1. Notice, two different input values. -1 did not equal +1, right? But, well, the y values, if I call this function f of x, f of -1 was equal to f of +1. So this fails. A quadratic function is not a one-to-one function because notice the y values repeated for different my husband was calling and I ignored his calling. He's like, oh, you must be recording. Anyways, let's come back. Or equivalently, if what am I reading this time? Let's go ahead and read this part. If they have the same output value, if they have the same y value, then what we know is their input value must be exactly the same. So this is just a little fancier way of writing down, hey, x's cannot repeat, y's cannot repeat, and different x values must have different y values. So let's look at examples down here to determine whether a function is one-to-one. First of all, let's see if they're even functions first. To see if they're functions, what I'm going to do is I'm going to go ahead and just look at the x values. X is 1, 2, and -2. So is this a function? Yes, this is a function because it has all different x values. Let me look at the other ones too. -3, 1, and -2. That one also passes the vertical line test. All the x values are different. 4, 6, 2, and 0. All the x values are different. So that one is also a function. 1, 3, and 4. So, you know, A, B, C, D, they are all functions. And maybe I should have just trusted that, that they called all of these function. But now let's go in and see if they are one-to-one. If you want to see if they're one-to-one, what you need to see is check out all their y values and see if they're all different. Now, y values are 4, 3, and 4. Notice 4 repeated, right? So, because 4 repeated in the range, this is not a one-to-one function. This is not a one-to-one function. And if you graph this, you can try to graph this over here. Let me plot these. 1, 1, 2, 3, 4. I'm going to have my first point right here. 1, 2, 3. So these two are okay. But if you put the last point, -2, 4, notice these 2 points are on the same horizontal line. It fails the horizontal line test. Fails the horizontal line test. I'll just call it HLT. Therefore, A is not a one-to-one function. It is a function, it's just not one-to-one. All right, let's look at B together. Highlight all the y values, 4, -1, and 4. What do you think? This is not a one-to-one function either. Why? Because, again, that little 4 repeated, not a, you know what? Instead of spelling one-to-one, you can say 1, 2, 1, like this way. Not a one-to-one function. And you can graph this, and you will see 2 points that has the same y value. It's gonna fail the horizontal line test. But as long as you can see that, you know, one of the y values repeated, then it's not a one-to-one function. Now let's look at C and D. C, -5, 6, 4, and -3. Notice all the y values are different, right? So if you plot this, if you graph this, then it's gonna pass the horizontal line test. So this one, yes, is a one-to-one function. Why? Because all the y values are different. Let's do the last one. 0, failed it. 0, 0, and -5. This one failed it. Let's graph it just for the last one. So 1, 0 is over here. 3, 0, 1, 2, 3 zeros over here, and 1, 2, 3, 4, 1, 2, 3, 4, 5. Now this guy all the way down there, that one is okay on his own, but if you draw a horizontal line right here, it's going to fail the horizontal line test, these 2 points. Therefore, this is not a one-to-one function. So that's how you can tell if a function is one-to-one, okay? So basically, it is a function. If you flip your domain and range, it still works as a function, okay? All right, so I've been talking about this horizontal line test here. And so the bottom of the first page, we're just going to go into it. A function defined by y equals f of x is one-to-one if no horizontal line intersects the graph in more than 1 point. So what we're going to do is, given these 4 graphs, I got 1, 2, 3, 4 graphs, let's draw some horizontal line test to see if this given picture is a function. Now, first of all, Isn't this guy the absolute value function? This is an absolute value function. But the question is it a one-to-one function? So draw that horizontal line right here. Boop. Notice how it touched 1 point and 2 point. It failed the horizontal line test. Failed the horizontal line test. So what you can say is this absolute value function is not one-to-one. Okay, let's try the next one. This one, the second one, looks a lot like a cubic function, doesn't it? Because it has, well, I can see 1, 2 clear turning points right here. But you know, just to be safe, I'll call it a polynomial function. But let's draw a horizontal line right here, anywhere in the graph, and it needs to pass. Because you know what? If you move this, let me see if I can move this. If you move this horizontal line up, like, it's gonna pass the horizontal line test at that point. Where else? It's gonna pass the horizontal line test at that point. But you know, it has to pass everywhere on the graph. So if you draw a horizontal line there, you have a 1 point, 2 point, and 3 points. So definitely this graph also fails the horizontal lines test. If it fails the horizontal line test, this function is not one-to-one. Okay, let's look at the next one. Well, this one is a linear function. Let me draw a horizontal line anywhere on this graph, and notice how it touches this graph only once at any point. So if I move this horizontal line, it's just going to touch this graph once everywhere. So this one passes the horizontal line test, passes the horizontal line test. Therefore, this is a yes. This is a yes one-to-one function. Okay? Now let's look at this circle. Well, first of all, is this even a function? Now, I'm not doing a horizontal line test right now. I'm doing a vertical line test because this guy doesn't even meet the condition to be a function. This is not even a function. So if it's not even a function, we cannot call it one-to-one function. Because listen, guys, function is the big set, okay? And the one-to-one functions are the special guys. So to be even considered a one-to-one function, it needs to be a function first, okay? So without even doing our horizontal line test, we know this is not even a function, so there's no way this is a one-to-one function. But, well, say that you still try to draw that horizontal line. How many points does it touch? 1 point and 2 point. It fails the horizontal line test. Well, let's add that as well as the vertical line test. Therefore, this is not one-to-one. And add a little more. Not even a function. Okay? So that's how you can use the horizontal line test to tell whether a function is one-to-one. Okay? All right, let's go on. You know what? I'm going to come back to objective 2. This one does take longer time every year. So, you know, I'm going to go down all the way to objective 3 where I will show you how to find the inverse functions. And then I will come back and talk about how to verify them. Okay? The example, the classwork problem that I will assign for 3.1 is similar to what I'm about to go over with you. So let's find the inverse functions. Now the graphing one is easy. If you want to just graph the inverse, first of all, take a look at this notation for me. Okay? It looks like f with an exponent of -1. Okay? This is just a notation for inverse function. This is inverse of f. Or you can read it f inverse. Okay, so below is the entire graph of the function f. So here's my little f. They want you to graph the inverse function, the inverse of f inverse. Let's go ahead and do that. And this one is similar to what you will do on your homework. What I suggest you do is you just plot a couple points on this graph. I got 1, 2, 3, and 4. And let's use that same strategy that lady in our little demonstration used. Now I'm going to go find all these ordered pairs. The first ordered pair is at, what's that one? -3, -5. I'm writing down all the ordered pairs. Now this one is at 2, -4. This one is at 7, 2. And the last one up here is at 8, 7. Now, let's do that little table thing. So this is our f. This is our f. F had -3, -5, 2, -4, 7, 2, and 8, 7, right? That was the input and output of our F. Now let's go ahead and find the input and output for its inverse function. And remember how she did it in her video, right? Our x's are going to be now y's. So you switch -3 and -5. So the first input will be -5. The first output will be -3. You switch x and y. So the second point that I will need is -4, 2. The third point that I will need is 2, 7. And the last point that I will need is 7, 8. Now we're going to plot these 4 points on the same graph. And remember what we want to see? We want to see a nice symmetry with respect to the line y equals x. Alrighty, let's plot these. -5, -3. -5, -3, right here. Next one, -4, 2. Right here. Next one, 2, 7. 2, 7. And last one, 7, 8. Right here. Let me connect them with lines. Whoopsie, that wasn't too pretty. This, and that. Now, do you notice, let me try to sketch a y equals x line with this green highlighter. Now, imagine folding this graph in half. Oh, I'm sorry. Imagine graphing or folding this graph by that green line. You see how this graph is symmetric with respect to this line y equals x, right? This is our line y equals x. We just graphed the inverse function using the given function f. So, graphically, I think you got it. That's not that bad at all. But I want you to remember this. What did we do to find the inverse function? We switched x and y, didn't we? That's what we're going to do, even in algebraic case, okay? So procedure to find an equation of an inverse function. I got the steps down right here for you. Step number 1, if they give you the function name f of x, just change the f of x to y so that you have x and y in your equation. Step number 2, just switch x and y. That's going to be the important step. Switch x and y, and then you will solve for y. Once you're done solving for y, just give them that fancy inverse notation, and then you are done. I'm going to go over example 5, 6, and 7 with you. And then I will assign a problem similar to number 7, okay? Example 5. So they want you to find the f inverse where... The f inverse is the inverse of f. Okay, so what's step number 1? You need to switch this f of x to y, right? So write down y equals x minus 5 to the 3rd power. So we did step number 1. Now, what's step number 2? That's going to be the most important thing. You need to interchange. X and y. So switch x and y. So take a look. Where you have y, you're going to have... everybody's trying to reach me today. Change the y to x. Change the x to y. And then copy down, everything else exactly the same. Notice what I just did? Interchanged x and y. That's what I just did. Okay, now what's step number 3? You need to now solve this for y. So let's try to solve this for y. First, we need to get this guy out of that cubing. So what do we do to both sides to get rid of cubing? Well, we're going to take cube root of both sides. So let me write this down here though, because if somebody's just reading the notes, I want them to see the step-by-step. Not square rooting though, but cube root both sides, okay? If you cube root both sides, you will get cube root of x on the left side. And let me highlight what's about to cancel out, guys. This cube root and this cube will just cancel out. So what are you going to have? You're going to just have the y minus 5 out, okay? Now, the last step. Add 5 to both sides. Then you will have cube root of x. Remember to keep that cube root short. We don't want to extend it all the way over. So only thing that's under cube root is x. But remember, we're going to add 5 to both sides. So you will have something like this. Now this is good. You're actually almost done. But what is step number 4? You just want to give that fancy inverse name back. So let me write the fancy inverse notation. It's not that bad. I'll write f inverse of x. So we're replacing y with that notation is equal to cube root of x plus 5. And that's the answer. This is how you write your inverse function. And this one, if you see your function has cubing, your inverse function better have cube root operation, right? So that's our first example of writing an inverse function. Let's try a couple of other types of functions. Now this one, well, look, my f of x this time has cube root. So later, when we write the inverse of f, we will have cubing involved, right? So let's try this one together. So first of all, change your f of x to y. You get y equals cube root of 5 minus x. And then notice the plus 1 is outside, right? Now, this is a great start. Let's switch x and y. That's step number 2. X equals cube root of, what's inside? 5 minus y plus 1. Now we're trying to solve for y here. What we just did for step 2 is we interchanged x and y. We interchanged x and y. Now let's solve for y. Now solve for y. Okay? Solving for y, I need to first subtract 1 from both sides, right? So if I do that, I will get x minus 1 equals cube root of 5 minus y. Everyone okay? Alrighty. Now we're going to get rid of that cube root. How can we get rid of the cube root? Well, we're going to have to take cube of both sides. Notice I'm cubing both sides here. If I do that, the left side is now x minus 1 getting cubed. Notice that binomial is not getting cubed. We're not going to write it as x cubed minus 1 cubed. Put that x minus 1 in a parenthesis and say that whole thing is getting cubed. Now notice, if we do that, this cube root and this cubing will simply cancel out, right? So you will just have 5 minus y left. All right, we're almost done. We're going to subtract 5 from both sides. Then, now this is going to be a little messy. Just because we have to subtract y and divide everything by -1. Yeah, let's do it that way. Yeah, we'll still do it. Subtract 5 at this point. Then you will get what? X minus 1 cubed minus 5 equals negative y, right? Nasty, that y is still negative. So we're not completely done. We need to divide everything by -1. Let me move the work over here, okay? And I think you can do that. If you divide everything by -1, let me show more work. I have room here. It used to be -y equals x minus 1 cubed minus 5, right? Notice, guys, I am about to divide everything by -1, divide this by -1, divide this side by -1. Technically, I have 2 terms on that side. So what's that going to turn into? I'm going to have y equals a negative x minus 1 cubed. Notice I'm changing the sign of that entire term. Okay, I'm not changing x to negative. I'm not changing -1 to positive. I'm just putting a negative in front of it. Now, -5 divided by -1, that's going to turn into plus 5. So we're done writing the inverse function. Oh, I almost put f prime of x. F inverse of x is equal to -x minus 1 cubed plus 5. So that's how you can write the inverse function. This one was a little bit messy because we had to deal with that negative in front of y in the very last step. But the idea is still the same. You first write f of x, give that function name, take that away for a second, just write it as y. You interchange x and y, and you simply solve for y. You see how everybody's trying to text me this morning? Guys, I'm going to go ahead and finish example 7, put a problem for today, and then I will come back and record objective 2. the verifying inverse functions in just a second. I'm curious why everybody's trying to, is something happening in the world right now? Maybe something's happening every day nowadays. All right, let's try example 7. This will be the last one in this video, but you will, I'll ask you to try a problem, okay? And then I'll come back and do the other, the page that I just skipped. Now, one-to-one function g is defined below. Oh, this is going to be very interesting. I love this problem. I will ask you to try something similar to this. They want you to find g inverse of x, where g, where that is an inverse. Also, they want you to state the domain and range of this g inverse in interval notation. Okay? So we're going to do the whole thing. Now, first of all, before I even get there, take a look at this g of x for me. In g of x, what is that one value that x cannot be? X cannot be equal to -8. Why? Because if you plug in -8 in here, you're going to get a negative 0 for the denominator, right? So using that, I'm going to find the domain of f. Domain of, g. Domain of g is everything except for -8. So in interval notation, now, that part is covered in Unit 2 exam, so I know you know how to do that. The domain of G is -infinity to -8, union -8 to -infinity. Now, I found that, but you know, the way that I asked you to find the whole, the range of a rational function in the previous unit, I asked you to use the horizontal asymptote and first see if that function crosses the horizontal asymptote, right? Now, I'm going to show you a slightly easier way, okay? And maybe if you didn't take your exam, because one of my section is taking it Monday, maybe this method will work. What we're going to do is we're going to now find the g inverse, okay? So let's find the inverse first. Change the g of x to y. So write down y equals 4x minus 5 over x plus 8. Now, let's switch the x and y. So I'm going to go ahead and highlight all the x and y. Now, you notice that I have y on the left side. So change that to x, okay? Now, on the right side, I got 2 x's. Both of those x's needs to change to y. So change the numerator to 4y minus 5. Change the denominator to y plus 8, okay? Now, we're going to solve for y, okay? Now, what are we going to do to both sides? Let me move this work a little bit to the side so that I can show you what I'm doing to both sides. I'm going to multiply both sides by that denominator. Multiply both sides by y plus 8. If you do that, what will cancel out? This y plus 8 will cancel out. And I will distribute this left side and make it xy plus 8x equals what's left on the right side? 4y minus 5. Okay? Now, don't forget what we're trying to go. We're trying to solve this for y. So if I'm trying to solve this for y, it makes sense that I'm going to gather all the terms that have y to the left, right? These two terms have y's to the left. So I'm going to move that 4y to the left side. And I'm going to move this 8x that doesn't have y. This one will just go join that -5 on the right side. So I'm just solving for y. And in order for me to do that, I'm just organizing where I'm moving all the terms that have the letter y to the left side. So notice, I'm going to get this, okay? I will have xy. Notice that one just stays. But this 4y that I'm moving, this one will turn into a minus 4y. And now it's on the left side. Now on the right side, I will keep that -5 that was still, that was there. But if I move this positive 8x to the left side, I will get -8x. Looking good so far, right? Now, why did I move all the terms that I have y to the left side? Well, because I want to now factor this out. I want to factor this y out in front of it. So what's left inside? I'm going to have x minus 4 inside. And the right side is still -5 minus 8x. Almost done. We're solving for y, right? So what do you do to both sides? You're going to divide both sides by this x minus 4. If you divide both sides by x minus 4, the x minus 4 will cancel out, right? Now we got it. We got the inverse function right here. Let me write it down here. We got y equals. Now if you want to write this term first, -8x first, that's okay. I think I will. -8x minus 5 divided by x minus 4. This is the inverse function. So let's give them that name. G inverse of x is equal to negative 8x minus 5 over x minus 4. Notice this inverse function cannot have x equals 4, right? Why? Because if x is 4, this function will be undefined. So let me give them the domain. The domain of G inverse is everything except for 4. Okay? So I'll write that as negative infinity to 4 union 4 to positive infinity. Now they also wanted the range, right? Now remember that. The cool thing about one-to-one function, the inverse function, is that we got this inverse function by switching x and y. Remember I asked you to find the domain of G? Domain of G, what used to be the possible x values, are now the possible y values of our inverse function. So what you can do right here is this. You can simply say that the range of G inverse is the domain of the original function G, which is what? Negative infinity to negative 8 union negative 8 to negative infinity. So that's a cool way for us to find the domain and range of this inverse function. I don't think they ask for the range of the original function, but what you can say is that domain of G inverse is the same thing as the a domain of the G inverse is the same thing as the range of the original function. And we'll talk about this more and more. But I do want you to try a similar problem based on what I just went over with you. Sorry that I went over just one problem like this, but I think you can do it because I know what you're capable of. You're very good. So after watching example 7, I will create a problem that looks just like this and post it on Canvas. I want you to try that problem and submit it for me, okay? I'm going to stop the video for right now. Check out my phones because I got so many messages. I don't know what's going on today. But I will come back and probably do a little shorter video where I just go over the second objective on determining whether two functions are inverses. This one will be about like 20 minutes. But for right now, you